Oh, 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 oh. Yes, yes. Uh, uh, oh, okay. And then can I use? Oh, okay.
Very precious days to start from. Can experience. Beginnings, let me briefly. So Tetsuo got his PhDs from Kyoto University. Then has done several postdoc researches in the US and then actually professors in University of Washington too, but then next year he went back to Japan, University of Cuba and Kyoto University. 2000, against the full professors in Tokyo. Then 2012, he moved to the RIKEN Shina centers. Later, he actually established the interdisciplinary radicals and programs, and he is now the executive director of science. And as some of you know, that Tetsuo, the worldwide renowned physics, several groundbreaking works in physics, high energy QCDs, especially on sun rules, lattice QCDs, Quarkonian physics, heavy ion collisions, etc. And he has received numerous prizes, so I won't mention all of them. But last year, he has been elected as the international honorary members of the American Academies of Arts and Sciences. So let's welcome him. Yeah.
Okay. Thank you very much. Right. So it's my pleasure to give a colloquium. My first time to come here, although I came to Taiwan several times already. Okay. So today, I'm not sure the how wide the audience felt is. Today, I'm going to tell you a little bit about from Quarks to neutrons. So between elementary particle physics and then the astrophysics, how they are related. And then the connection recently came up, the collision between stars that was discovered in 2017. People measured not only the gravitational wave coming from, actually there's so far only a single. Also, they measure gamma rays, and That's called a multi-messenger. So what I'm going to tell you today is that how this kind of multi-messenger astrophysics tell you about uh, high density matter. The outline. So I talk a little bit about the phase diagram. If you are condensed matter physicist, you know the phase diagram, right? As a function of temperature, chemical potential, purity, and so on. So a phase diagram where state of matter is located. So that also that kind of phase diagram you can draw in very preliminary. Then I will focus mostly on the dense, very high density, like Newton. Then I'll touch on a little bit about measurement of the merger, this kind of event, gravitational wave coming from. Then finally, I will talk about the connection gravitational, then state of matter, high baryon. Okay, but just for just for the introduction, what are we made of? And then this is sort of the introduction to the undergraduate student, but still, let me just flash to you. So I just start from the galaxy. But that's besides stuff in this. But what I'm going to focus on today is something microscopic world where and also the nucleon, but not get into the string theory or those kind of smaller size of. So kind of area governed by so-called quantum chromodynamics. Then just remember that the proton and neutrons, which you know, the typical size is 10 minus 30, very called 1 Fermi, 1 femtometer. Then these nucleons has attraction with each other from a typically a size of 10 order of one order of magnitude larger, so minus 12. Now, CD, as I said, the theory governs the structure of the, like here it's a quarks bind together to form protons and neutrons with size of 1 Fermi. Then there's some so-called nuclear force which binds size is something like 10 Fermi. But if the number of nucleons more and more, they tend to the 54 number of nucleons. Then you end up with a which is gigantic actually. So what I'm going to talk today is the internal structure, especially the central part of the 10-kilometer size. And then interesting thing is that all these objects, like from nucleons to neutron stars, all governed essentially by the quantum dynamics. Quantum chromodynamics, just write Lagrangian or Hamiltonian, just one line, just like QE, except that the gluons, that to the photons, has some internal degree called color. Then you have a quarks. Then quarks coupled gauge field, some couplings. In the case of the QE, of E, that you have much stronger than coupling. Then you have a mass term for kind of Lagrangian was first by Nambu. Then this has a, although I'm not going into the details of this analysis of this Lagrangian, but it has a very high symmetry, like this is one kind of very large number of symmetry. Part of it is a color gauge symmetry, and then flavor symmetry. Quarks. For example, the proton have a U quark, and D quark, red, blue. colors, while neutrons, instead of U, you have a U. For lambda particle observed in, it's, yes, up quark, down quark, and string. Those kind of a combination, a lot of composite particles, which is called hadrons. Hadrons mean reflecting particles. That has been known for a long time. Now, one of the powerful approach solve the properties of the hadrons, so-called lattice ab initio approach, like a condensed matter ab initio approach, solves the equation directly by using some neutron method. The case of the lattice regularization that you discretize space and time, lattice structure, square lattice structure, calculate essentially the various observables using Monte Carlo method. Now, today I'm not going into the details of the lattice QC approach, but this approach is very powerful. Then, because of the big computers, like for example, we are using the Quarks supercomputer in RIKEN, where I mean 440 petaflops machine. Already was number 6 or 7, but when it was built, 2020, it was number 1. By using this kind of supercomputer, a little bit busy figure, but as I said, there are lots of composite particles, quarks, or quark-antiquark, that's called a meson. Then these lines are the energy of these mesons. Various bound state and excited state. Then by using this kind of simulation, with some input, you need actually a 3 coming from some mass of some particle, like pion K. You can predict all these triangle, red one are predicted the input. And really, it's within 1% or less than 1% level. You can predict the mass of the hadrons and also various other properties. So, hadron properties are understood, almost understood, at least numerically. That is good. The current state. Now, then CD done, and actually not, because 3 quarks, a quark, anti-quark, it's a few body system. But if you go to the many fermions, like condensed matter science, you know the electron, single electron properties cannot predict the superconductivity because of the many body interaction, many body physics state of matter. That's what we are discussing. So, talk a little bit more about this phase diagram. What I'm going to discuss is the many body problems, like many body problems in electrons, or many body problems in cold atoms. This is the many body problems of quarks. And then, as I told you, that the hadrons are just a few body systems, like quark, anti-quark, or 3 quark, and those. The temperature axis, the chemical potential axis, baryon chemical potential. So chemical potential at 0 temperature is that the how much energy you need one proton or neutron into. That is the case. So this can be replaced by the baryon density plane. At 0 temperature, a very low temperature, at very low density, of a few hadrons can be described very well by lattice QC. But if you go to the chapter system, like very high temperature, then this is a relativistic system. Therefore, if heat up the system, the vacuum, then you can get lots of quark, anti-quark virtual thermal excitation. Eventually, you have lots of quark anti-quark plasma. That's called a quark-gluon plasma. At very high temperature, so you may have some phase transition or sort of the crossover from the hadronic plasma phase at certain temperature. And turns out around 150, 10 to the 12 Kelvin, very high temperature from the standard, I mean, the daily standard, but typical energy scale. On the other hand, if you go to the very high density compressor system, hadron, then eventually they melt. Then they percolate. Then eventually you get the quark matter, where you have lots of quarks on the Fermi surface. Therefore, the system of degenerate quarks. Because of the interaction between quarks on the Fermi surface, you also develop a superconductor. That's called a color superconductor. Not the usual because of the color interaction, conducting. And then, but even if you have a superconductor, you have a very high temperature, then it melts. Therefore, again, you plasma. So this is a cartoon figure. Still, we don't understand what is exactly the phase and what is exactly the location of this phase change from hadrons to color superconductor. But I'd like to extract some information from physics point of view. At very high temperature, very low density, the Big Bang is actually the place where this quark-gluon plasma is realized. Also experimentally, by having a heavy ion collision like red or gold, large hadron collider, sun, or heavy ion collider at 7, they measure transition hadrons plasma. There are lots of evidence that that kind of phase change happens from low temperature to. So this part is quite explored experimentally. Also at very low temperature, but many new, nothing but the usual nuclear. There are a long history study of this. If you go to the higher density, then you eventually end up with neutron star is actually sitting. Actually, the central part of the neutron star is between hadrons and quarks. Therefore, we don't know what is going on deep inside the neutron. That is what. So let me just go first the high temperature direction. From here, the vacuum, a very high temperature. What should happen? This is the equation of state. The equation of state is, say, for example, the pressure of the system as a function of temperature. This is this characterize the system under the change of the. And then you remember the undergraduate textbook, the Stefan Boltzmann limit. Pressure is proportional to the force, temperature to the force for the photon gas. Similarly, at very, very high temperature, pressure over the T force becomes constant. Stefan Boltzmann limit approach is constant. Then it's a gas of quarks and gluons. On the other hand, if temperature is low, then you have a gas of composite particles like pion. Then you have it's called hadron gas or hadron resonance gas. So pressure is much suppressed. There is a transition from the suppressed pressure to the unsuppressed pressure around certain temperature, critical temperature. If you model this part only by using hadrons, then you overshoot air pressure. Calculate some in the perturbation theory. You can calculate some pressure in quark-gluon gas, but again you overshoot. That's because, theoretical calculation breaks down in. Actually, the red one is the correct one, which has been formed by lattice cube. There are 3 lines, but let's look at only pressure. So now here it's 3 times pressure over T to the red one as a function of temperature. Then near the critical temperature, I can tell you why later, if necessary. How did you extract this critical temperature at this Q? But it's very precisely known for the shoot critical temperature, 100 plus minus 1.5 ME. Then there is a transition from the hadronic gas to gluon gas. But there is no jump or anything. There is called the crossover. Crossover from the hadronic phase to the that is established. So historically, you have a gas of the ions or hadron. Then at the high temperature, you have a gas of quarks and very complicated. Right? Composite particle gas becomes a uniform quark-gluon gas, and there is lots of non-trivial things happening. That is very difficult to calculate analytically. But on the lattice, how they so this axis is fine. But this axis almost nothing known except for the nuclear physics. Again, you can symmetrically write the pressure as a function of the chemical potential. Again, Stefan Boltzmann limit at very high density, the free gas of quarks, degenerate quarks. Then it should behave like new horsepower for the massless quark. Then it should again sort of the similar to the Stefan Boltzmann. But at low baryon density, low chemical potential about nucleons, then you build up some pressure because of the interaction between. But again, you somehow overshoot. Then if you start from matter size, overshoot the real pressure, behaves something like this. The red one, the real equation of state, hole-free. Unfortunately, because of the okay. So here is a nucleon gas. Then you have lots of interaction, change of quarks, and but unfortunately, low lattice QCD calculation possible because of the so-called sign problem. Usually, similar to the condensed matter system, if you have fermion, then with finite chemical potential, then usual Monte Carlo breaks down also cancellation of lots of plus sign, minus sign, or number. So unfortunately, possible. Therefore, we cannot draw a very precise line like this one. That's why we now ask data from neutron stars how this will. And actually, the central part of the neutron somewhere. Therefore, may be able to get some information from data. Of course, the other theoretical way is just abandon Monte Carlo simulation, then use some computers essentially use Hamilton diagonalize. Therefore, you don't have sign problem. If you have high performance, may be able to in the future calculate kind of first principle. But it's so neutron stars. What's the connection between dense Qs and neutron? Let me show you a little bit more about what is neutron. Mass of the neutron stars observed is something around 1 solar mass to the 2 solar mass, a little bit more than typically the size of the sun. Radius is typically 12 kilometers. And mass density by using this, we calculate average mass density 12 kilogram per cubic. That's huge. I mean, on Earth, it's just 1 gram per cubic centimeter, something like that. So it's a density, very super high density. Then inside, density is higher than the average. Therefore, higher than, or several times higher than the atomic density. Atomic nucleus is very dense. I just go. Atomic density is also high, but the neutrons inside is higher than atomic. That means they compressed more, and then eventually it may become a quark matter instead of the nucleonic matter. That's what. So and people have already studied what is the structure from outside to the inside. And of course, outside density is low. Therefore, we have a lot of knowledge, the physics, atomic. Therefore, we know better outside, but we know almost nothing. We have a few centimeter atmosphere, like hydrogen, carbon, depending on. And then you have a surface composed of atomic nuclei, solid. Have a bigger lattice. Then if you go inside a little bit more, then you have a region so-called a crust, where you have atomic nuclei, just like this solid structure, but some neutrons coming out from the usual nucleus, then becomes a superfluid. So it's a solid, but you have a liquid neutrons floating around together with the electron. That's called the crust. And then if you go even inside, then the nucleus are compressed and then completely dissolved, the neutrons and protons. Furthermore, neutrons become superfluid, protons become superconductor. Those features can be predicted by using the knowledge, therefore, the common, knowledge of. But even inside, protons and neutrons, just further comes quark matter, hopefully or possibly, with color superconducting bit. But that we don't know. Actually, the size of the crust from the surface is 500 meters. So you dig 500 meters or so, then you find the outer core where you have the liquid. So it's rather unique. So it's not just like Earth, the interior of the Earth, which is much more complicated. But here, in some sense, simpler, but unknown. What is the size of the neutron star? It's kilometer size. Type A, actually something like this size. Yeah, we are now here. Of course, you cannot do this because if you, the mass of the neutron star is of order the sun, right? So all the Earth is absorbed into the neutron star, so you cannot do this. But the typical size is sun. Okay, so here is some history of the neutron star observation. Of course, neutron stars is composed mostly of with something like 10% of the protons. That is a typical, But neutrons has been covered by Chadwick, 1930. Then only 2 years later, the Barde and Zwicky astrophysics, but there may be a star composed only of neutrons after the supernova explosion. Amazing. Then 34 years later, the pulsar was discovered, and it turns out it's a rotating neutron. So pulsar is a neutron star, but and then rotating the axis, rotating. But on the other hand, have some magnetic field, but the dipole type. That's not really a dipole. Actual probably, but suppose it is a dipole. Then the dipole is rotating this way. Then it radiate photons or bands. Then they have there are huge measures. kind of pulsation turns out that can be radiated on. Then and then other. Yeah, that's really a scandal. Everybody. And now 74. There was a discovery. Again, this is Nobel Prize, but the binary neutron star was this. There was a stellar binary. The interesting that their rotational frequency comes higher and higher as you measure. I'm sorry, that's a very small figure. Changes comes higher because of the radiation of the gravitational wave. It does not rotate in this way, but it rotates center. Then the frequency becomes higher, and that prediction of the general relativity, the line here, not a fitting line, predict the rotational frequency from general relativity. So it's a test of. Then 2010, there was a discovery of the massive neutron star, massive around 2 solar mass. So I mean, for that time, typical neutron star mass was found to be around 1.4 solar mass, but here it was discovered that around 2 solar mass neutron. Then that was a shocking news because it related to the equation of state of the neutron star inside. If the neutron star equation of state is very soft, soft means pressure is low pressure, then you can compress the neutron and then collapse into black hole. So the equation of state inside determines the mass, maximum mass of the neutron. Then up until this time, we thought that probably the maximum mass of the neutron star would be at most 2 solar mass or so. There would be no neutron star which is above solar mass. Otherwise, non-equation of state is pretty ruled out. Turns out that the 2 solar mass neutron star was discovered. That means that the pressure is relatively high inside neutron star, means that the core part of the matter is relatively stiff. Although it may not be a solid, but even if it is a liquid, rather stiff equation of favor really describe this kind of tool. It was discovered by so-called Shapiro delay method. Very interesting, but I'm not going to do it. And now 2017, I think 2015, LIGO discovered the merger of the 2 black holes. Years later, LIGO-Virgo collaboration discovered neutron star merger does collide. So yeah, if you wait enough long, then this will merge. Then by emitting wave. This is the frequency of the gravitational wave, originally from 50 Hertz or so, and then it becomes 1,000 Hertz when they, and that was measured. Also, 2019, the light bending around pulsar, which I'm going to tell you a little bit later, by the nicer X-ray. That gives you also a constraint on the mass and weight. So there are lots of discoveries after 2010. Of course, not only this one, but there are many others. But these are the typical discoveries, key discoveries. That's why now the neutron star physics is very hot. So let's move on to the how the gravitational wave is emitted. Roger. But yeah, bring yes. August. So this is a gravitational wave 2017, August 17. So it happened on August 17. And then after that, originally, I mean, gravitational wave is a gamma rays emitted, and after that, it becomes bright. Second, you have a very bright, I think optical. Then it becomes later. is galaxy NZ4993. I don't know. But the 44.1 megaparsec, 44 mega light year away, very far away. But still, you could not only by the gravitational wave detectors, this yellow one, but also space telescope and the telescope. This is the first detection. As I already showed you, the time scale, the merger, this is the point where they merge together. Eventually, they merge together and then rotate a little bit, and then becomes a black hole. But, so this is just before the formation. I mean, big thing. Then the gravitational wave frequency becomes higher and higher. Yeah, they merge. Then 2 seconds later, various energy scale, say, let's see, KB, the gamma ray from Fermi satellite measured. So they merge, then they create a gravitational wave, and then 2 seconds later, they create gamma ray, and then later you have a lots of other. So this is just a cartoon by Daigo. But after they merge, they there are lots of materials ejected outside space. Then there will be a nucleosynthesis. You may create some heavy elements like gold or platinum. Then that is under debate whether neutron star merger is enough to create heavy elements, or neutron star black hole merger is more relevant, and that is under debate. But this is for 2017. But there was a prediction of this one already 2010 by movie and also the music. Actually, may know or may not know the British rock band. They have a song for this. Then I would like to ask, play a little bit. Hope you can. Only a little bit. Okay, so that's it. This is yeah. So actually, this rock band created not only this neutron star collision song, but also supermassive black hole. Also, they have a song like supermassive black hole, and yeah, various things. So yeah, you may want to check. Anyhow, okay. So this is a real neutron star simulation by one of the experts called the merger and gravitational wave by numerical relativity. You solve the Einstein equation directly, numerically. Of course, you need some equation of state and so on and so forth. Station is for the neutron merger, measurement. So people have been doing this kind of simulation for a long time. And now, at this time already, they could really make realistic, in this case, 1.4 solar mass plus 1 solar mass, 4 mass merger. It's the x and y axis kilometer. Size is, say, diameter is 20 kilometers. As you rotate, there is a gravitational wave rotation, already gravitational wave. And then they deform, then merge, and then rotate. Here it's they merge. Then you have a high frequency, typically 3000 hertz. Here it's up to 1000 hertz. eventually 1.4 plus 1.4 is 2.8, which above the the region where you can get black hole. Therefore, it becomes black hole. So people are debating where is the upper limit actually to make black hole, whether it's 2.5 or 2.7, 2.8. By certain equation of state, it becomes black hole. You have a very stiff equation of hard equation. Pressure is large. In that case, pressure is large. Inside pressure is large. Therefore, you cannot compress the neutron star much. Therefore, the size of the neutron star is larger. You have a soft equation of state. Then it can be compressed. Therefore, the size of the neutron star itself is smaller. And so suppose you have a smaller soft equation, then they collide with it. Then the size is small. Therefore, they touch at very late time. Therefore, you have a very high frequency gravitational wave. So depending on equation of state, the frequency of the gravitational wave different already for touching. So you can learn many things, even this region. Also, you can learn how neutron star is deformable. That's called a tidal deformability. That kind of number can be also constructed only from. But you can learn more also this region in the future. So far, people measure only this, not aftermath. Another observation, nicer observation. Nicer is the interior composition for ISS. I saw this ISS model just entrance. And so I was watching which is nicer, but I couldn't find this place. But if you find, please let me know. Okay. So this measure X-ray. What kind of X-ray do they measure? Neutron star, as I said, it's a rotating star, and then sometimes you have a hot spot. I mean, if it is a dipole magnetic field, then you have this dipole and then hot spot, north pole and south pole. But the actual neutron star, not like this one. Like a sun, you have lots of different hot spots. This is the hot spot. But you have lots of activities there. And it's rotating. Therefore, this hot spot, sometimes behind you, by looking at this neutron star from this side, the hot spot is behind you, or you can see the hot spot. But neutron star gravitational, gravity very strong. Therefore, even if hot spot is behind you, behind the neutron star, the light coming from the hot spot can bend, and you can see this. So by looking at this one, measuring very carefully, then you can make a constraint, the mass, the so-called compactness, mass over the radius, mass and radius relation, and you construct this. Then you can draw some constraint. If the radius is this, then the mass is this, and it's something around, if then maybe 12 or 12.5 kilometer, then in this case, the mass is 1 point. You can make this kind of constraint between mass and radius. So this is an independent determination of the of mass and radius. Other pre. Okay, so so by using I go to the connection between gravitational wave and this somehow related to my own work in the. So this is again the phase diagram in a different looking, but this is temperature and the chemical potential. And then at low temperature, low density of nucleons, have a nuclear matter, neutron matter. Then nuclear matter, neutron matter, there's some interaction, attractive interaction between. Then they make a. That has been predicted actually many years ago by this. At very high density, then they completely overlap and melt, have a quark matter. Then the quark matter, because of the interaction, attractive interaction of the Fermi surface of quark, you have a color super. You have a Cooper pair. Typically, Cooper pair is very large compared to the particle. It's like usual BCS super. But as density becomes lower, then you have to have some sort of the strong interaction which makes things protons and neutrons. There's something should happen. One possible possibility that this super pair becomes tighter and tighter and becomes almost like a bosonic dipole. Like very similar to the BCS crossover, the case of the atomic condensate. The fermionic atomic gases, if the interaction between fermions becomes stronger, then becomes weaker its BCS, but stronger it becomes a very tightly bound molecule. Then there's such kind of crossover from this. That kind of thing may happen. But in the case of the quark, only 3 quarks get together to form baryon. Therefore, this region is a sort of the Bose-Fermi mix. This is also a very interesting object that has been also studied in cold atomic gases, but there are similar things happen. So this is, of course, a scenario. This is already, established. This is theoretically established. Nobody has seen this color super, almost theoretically established. And what may happen in some Bose-Fermi mixture, a tightly bound pair with some fermion interacting with that kind of thing. So this is speculation. And then there are lots of works. I cannot list up all of these, but interesting thing is that when I write this curve, supposed to be a first order phase transition. And then we already know from lattice QCD simulation crossover, means that there is no first order line. This one touches it. There may be a critical point where you have a second order. The end of this first order line becomes second order point. Here is a cross. This is a very plausible scenario, high temperature. At low temperature, the first order line may touch here, that you may have some first order phase transition, or may open just like this one. Then they may be connected. There is evidence, theoretical evidence, that that can happen. That has been, I think, first proposed by Schaefer-Wills from the symmetry argument. Actually, if you look at the symmetry very carefully, then the symmetry breaking pattern here and symmetry breaking pattern actually, this is one going diagonal, left plus right, happens both cases. Therefore, there is no symmetry difference between. Therefore, that can be crossover. Of course, it doesn't say that it must be crossover. It can be crossover. Because it's a single phase. There's no distinction from the symmetry. And actually, we have done Randall type analysis, and then they found that it actually happens. Then that in new phenomenology area, the protons and neutrons from proton matter continuously connect to the quark color super. That kind of pattern. Actually, if it is a first order phase transition, then it's already current observation. Therefore, even if there is some first order phase transition, a very weak first order, or it may be a crossover. So that is the current state. In any case, neutron star is sitting just around here. Then below, it's a strongly interacting ionic matter. Side is strongly interacting quark matter. Therefore, it's both non-perturbative in the sense that you cannot really calculate in use perturbation. That's why we really need data at the moment. and wait for 10 years. And let's see. Huh? Oh, sure, sure, sure. Yes.
Continuity broken by the finite temperature according to plot.
Uh-huh.
So on the theoretical side, would you really estimate temperature there?
No, at the moment, no. Yeah. So what we have, I mean, all these works have done is that there is a possibility of opening. That is all. Actually, and another thing we know is that if the strange quark mass is suppose quark mass in the real world is heavier, sorry, lighter, then this approach is down. So depending on the quark mass going up and down, but how much we don't know. So to calculate this neutron star structure, we usually solve the general relativity, Oppenheimer-Volkoff equation, where you have a mass and pressure. So it's a relation between the mass, energy density, and pressure. There is only two equations. Then you need to supplement this equation by the equation of state, pressure as a function of the energy density, really solve mass of as a function. I think I run out of, I think, a little bit time, so I'm going to yeah, but still I and a little bit about the equation of state. So at low densities, very low density, you have a neutron. This is a Fermi level of neutron. Neutron are all, but not just the neutrons, because neutrons and protons, because of the weak interaction, they go in, neutron decay into the proton, proton going back to the neutron. That kind of beta equilibrium happens. Then there are some neutrons, main fraction is neutron, but you have some 10% fraction of plus electron. That is a low density. At high density, very high density, have a U quark, D quark, S quark with different Fermi level, but essentially, I mean, there are almost equal mixture. We don't. Okay, I'm going. This is very busy figure. I'm sorry. It's one very busy. So original idea of the application of this continuity hadron stuff phenomenon by us much before discovery of. Then detailed construction of that case at low density usually use chiral EF, high density super. Then we don't know, so it's super phenomenology. So we just interpreted this by using thermodynamics, and then apply this kind of merger simulation. I showed you what does the merger simulation. They use a phenomenological equation. Now, find the state with quark matter inside, then do real merger simulation, compare with the data. The equation of state, pressure, log scale as a function of the baryon density. So this is the nuclear matter density, the nucleus. So pressure is low at low density, high at high density, but the low, the hadronic matter, and high, the color super quark matter. Blue, and the red one are the theoretical curve. Then there are some constraints from the measurement, the gravitational wave, and also the nicer, and also the mass significance. Then this is not a fitting, but they are somehow consistent. What is important is that there is a crossover region where from the hadronic matter where you can identify single nucleons, but crossover region these nucleons start to overlap and then becomes a quark. the crossover region, you have a bending equation of, meaning that the equation of state has a very sharp sound velocity. Sound velocity is dpt, essentially dpt rho. So the derivative becomes large and then small. That the sound velocity. That is originally done years ago by my friend, but I'm not going now. So here is mass and radius relation. Mass over the solar mass. So here is the solar mass. This is the radius. Here it's something like 12. By using this crossover equation of state, this is the central density of the the unit of nuclear density. 1.3 times nuclear density, going up to this 0.5. Here already started to overlap. Then the very large mass, eventually you. Okay, so to understand this one, I mean, just forget about this red, green, and the yellow band. This behavior is easy to understand. The mass small, mass is small here. Then the mass, if the mass a little bit, then the mass, if you mass increases, then the gravitational attraction becomes larger. Therefore, star shrink. That's why it's going this. But this says that the from say 0.5 to somewhere here, even if the total mass of the neutron star increasing, the radius doesn't change so much, meaning that the inside you have a very stiff stuff there to hold the shrinking of the neutron. And then eventually mass is too large, then because of the very strong gravitational attraction, drops into black hole above this maximum limit. The measurement, solar mass 2.1 solar mass. You have to explain this. Should go over this. Band is coming from the constraint from gravitational wave, and also the. So still, I mean, constraint is very, but still, I mean, this is not a fit behavior. Very observation. So what this means is that there's something very stiff inside. Maybe quark matter or maybe something else, but we don't know what. But what we can imagine is something very stiff quark matter. Yeah. Oh, I'm sorry. Yeah, this is a central density of the. Yeah, so this is center of the neutron star. It's 3.5 times denser than the usual nucleus. At that density, you can calculate the particle distance, and it's already neutrons are overlapping. So probably, I mean, this region already quark matter is happening. Then how this is a single neutron star, but the neutron star merger, how that affects the frequency, that kind of thing. So how it affects this kind of frequency after the merger, that is the simulation by using our equation of state. Solar mass, let's see, total mass 0.96. So it, I mean, go to the black hole. But at the time, so this is 2.4 milliseconds after the merger. So it's already a big neutron star rotating. Then depending on the equation of state, you have some formed rotating big neutron star that emit the gravitational wave of, say, typically 3000 hertz. Then here it's a density, central, density for the nuclear matter density, more than 5. So this region likely to Quarks. inside the neutron. So nice thing of this merger event is that you can even compress the neutron star so that the region of the quark matter larger instead of the compared to the almost the last. So this is a nice plot proposed by guys. This is the tidal deformability, so-called tidal deformability, some unit. Actually, this is the dimension. Dimensionless. So tidal deformability is that how the neutron star can be deformed by the external gravitational potential, gravitational field. So two neutron stars rotating, then one neutron star is as an effect coming from the gravitation from the other side, then it's very deformed. But the deformation, how it can deform, depend on the equation of state of this neutron. So this is directly related to some equation of. And then this is the frequency of the after the merger. So this can be determined experimentally, observationally, before the merger, can be determined after the merger. So just a single neutron star merger event can measure both. And then theoretically, we have lots of different type of equation of state, but usual hadronic equation of state without quarks carry around somewhere here. But if you have a crossover to the quark matter, then it's the cross. Circle is the hadronic without quarks, and the crossover equation. Typically, the crossover equation of state has a lower frequency or given tidal deformation. So if you have lots of event, neutron star merger event, we expected it's 2017. Haven't seen the second one. Then originally people thought that maybe every year at least 2 events measured, but I don't know why. But there are so many black hole merger events. Just few days ago, I mean, measured the most massive, I think, total 240 times the solar mass. Right? Black hole merger data. Some merger event is only one so far. But if you can measure the lots of neutron merger events, then plot here, then we eventually come. But of course, need to measure high frequencies, 300 hertz, which cannot be done. Current LIGO, Virgo, Kagura. That's why in the future, this is I try to do it Chinese or Taiwanese. I hope this. So now Kagura, Japan, and then LIGO, Virgo working, and then there is a plan LIGO India. There is a plan of the Kagura update. And actually, I'm a member of Kagura these days, and then they are talking these days about around 2030 to measure high frequency part by focusing on the neutron star merger, so 300 hertz, 3 kilohertz region, to really down kind of physics. One of the Kagura's target around here, it's 5 years. I think still I'm alive, so. Okay, so let's summarize. So I have been talking about the merger, what kind of things you can learn from here. That's what and of course, cosmic observation, gravitational wave, electromagnetic wave, and also, I mean, in principle, you could neutrinos because I mean, a supernova 1987A, you could those, and why not in this? So those kind of continuous measurement for the multi-messenger. Theoretically, QCD, many body problem. And the few body problem, that's okay. But now many bodies problem, still difficult to do. So far we have been doing very phenomenological and try to learn something from this gravitational. But eventually, I want to do the other way, like nuclear physics, nuclear collisions, relatively low energy nuclear collisions make sometimes possible something like few times nuclear matter density. Therefore, we could simulate somehow by nuclear collision this kind of thing. Probably not RIK LHC, but JPAC, so-called JPAC high, heavy ion, or GSI here, other places. Here it is. And then I didn't talk much, but condensed matter physics is very much related to this one. Actually, the neutron star physics is very much related from the beginning to the condensed matter. And Phil Anderson and all those people have discussed the superfluidity, hypothesis. Then still, I mean, these days also, I mean, the superfluid hypothesis, the Fermi gas, very much related to this BCS crossover in cold atoms. And so this is also a sort of the simulator to and the field areas. So it's a relatively interdisciplinary area. And then it's very exciting to me. I was very much excited by the Coulomb plasma physics when I was a graduate student, 87, something like that. And then eventually they created big relativistic collider 2000. There are lots of data coming. Now we hope that the thing happens high density and the dense force. Okay, thank you very much.
For the very nice talk. So any questions from the audience? Maybe Shannon first.